grade 12 general practice questions, end of year focused, and I've reached generators. So an AC generator is something that creates electricity by moving a magnet or a coil. If you spin a magnet or spin a coil through a field, you will end up getting an induced current through Lenz's law. And if you want to increase the voltage or the current that you're going to get, to increase this, we will have to make a faster rotation. That will be good. The faster you go, the more you will induce. Increasing the strength of the field. Yes, a stronger field also means more induced EMF. Very good. Number of turns means more current can pass through the same coil. This is really good. Actually, all three are very nice. So this is a way to increase the voltage on an AC generator. I've got a separate video explaining how they work, so you can go ahead and watch that if you want. Otherwise, this is just for revision practice questions. So an AC generator, we are rotating, moving a coil. When you move a coil, you will create electricity. So mechanical energy, which is kinetic energy, movement, will give me electrical energy. So mechanical to electrical for a generator. Over here, now we have a coil, and now the field is decreasing. So now, there is a three-step solution for this one. I like to know all three steps. First things first is it going to be increasing or decreasing? So I'm going to think to myself, is it getting stronger or weaker? Stronger or weaker? Weaker. The reason I'm asking that is for the second one. Will the induced field be in the same direction? Same direction or opposite direction? That means if it's getting stronger, it wants to oppose that, so it will be in the opposite direction. If it's getting weaker, it doesn't want it to get weaker, it wants to bring it back to equilibrium, so it will end up being in the same direction. So stronger will be opposite, weaker will be the same direction. That's the induced field I'm talking about. And the third, you will decide whether it's going to be clockwise or counterclockwise. So every time you see something like this, it's a three-step solution. It says it is decreasing, so this field is getting weaker. If it's getting weaker, it's going to be in the same direction, which is a dot. And if you remember from above what I did, I had the dot and I have my fingers going around. This is going to be CW every time. And X is always going to be CCW. Sorry, wrong way. This is CCW and CW. Yes. This is counterclockwise and this is clockwise. In this case, dot we've established is going to be this one here. It's counterclockwise. Counterclockwise, B is the answer. So let's try that again. It's getting weaker, same direction, dot. Dot is out of the page is counterclockwise. That's why the answer is B. Into the page would be clockwise. Looking at this one here, the north pole of magnet moves towards a loop. We need to figure out the direction of the current. So this is the north coming in, it's entering. It's entering, so it's actually getting stronger. Stronger means opposite direction. So this is entering, stronger. Opposite of this is going to repel it. So I will put a north here, so it's pointing upwards instead. So now I have repelling. Of course, if a magnet is entering the ring, it has to repel it by pointing outwards. If it was leaving, you could attract it with the south pole. But no, it's north pole entering, repels with the north pole. So I'm putting an imaginary magnet here. So now, as viewed from above, so basically if I turn and I look at it with my big eyes, looking at it, that's my eyes, looking down at it like this with my eyes, I can see that this field is coming towards me. Towards me is out of the page. Out towards me, what was that again? Out towards me is counterclockwise. Out is counterclockwise. So I'm going to go ahead and pick C again. Counterclockwise. Okay. In this case, we are asking how to not produce a current. So remember from before, anything parallel is not good. No current will be induced at all. So towards the wire, it'll get stronger. There will be an induced EMF. Away from the wire, it's getting weaker. There will be an induced EMF. Moving parallel to the wire, this is the correct answer. Increasing the current means more EMF will be induced because it's a stronger field with the stronger current. So only parallel would not induce an EMF. They didn't ask us to find the directions, so I will not go ahead and do that. So the current below is here, so they've shown you the hand on it. That's nice. This is the hand that I keep trying to draw. And what are we trying to do here? We're trying to make the current go upwards. Okay, so if I want the current to go upwards, what I must do is, let's try it first of all. Let's put a north and a south here. If I increase the north coming into the field, this is going to oppose it. It's going to be a north coming out. It wants to repel with this. Because it's entering, getting stronger, it wants to repel. Thumb to the left, and my fingers going up. So moving a north towards it actually does work. Moving the south away, let's check, let's rearrange this now. Let's take my south and it's leaving. South is getting weaker. It wants to attract it. So with attracting a south with a north. So this will be in the same direction. The field happens to be in the same direction because north to south, that's not important. We just know that it's going to try to attract to bring it back. This is leaving and doesn't like it. It wants it to stay. So north, again, north, thumb pointing left, current going up 2 is actually correct. Let's look at the next one. Moving the north away. So let's get the north away. This is north, this is south. This magnet is leaving. North is leaving. How will it attract the leaving north? What will it do to try to bring it back? It will attract it with the south. South means north is on this side. And that means my current will actually be coming down the page. So that's actually not true. So this is the idea here about attracting or repelling. If it's entering, it wants to repel. If it's leaving, it wants to attract and bring it back. And of course we know north and south attracting and repelling, right? What's this? Type of electromagnetic radiation has the lowest frequency. Okay, so we have a whole bunch of them. I actually made you guys listen to a song and sing it so that you can memorize the order. It's a very annoying song, but it works. It starts off with the lowest, the biggest wavelength, smallest frequency, smallest energy. This ends up being radio waves, then microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. It's good to know if you memorize it. There's a little song that helps. So on the left hand side, biggest wavelength, smallest frequency, smallest energy. Obviously on this side it'll be the opposite, right? Smallest wavelength, biggest frequency, and biggest energy. What is it asking for now? Lowest, red light. Light is visible light, so Roy G Biv inside here. That's here. Microwaves is on the left. Okay, that's lower than this. X-rays is way over here. Ultraviolets are way over here. They're higher. So the lowest frequency happens to be this one out of these options. Radio obviously is the lowest, but that's not an option. The option will be microwaves. Very good. Okay. Now we need to list. Oh, okay. Well, I just did it, right? Radio waves. Smallest wavelength. Actually, let's check. This is flip-flop now, right? Smallest wavelength is here, right? Smallest wavelength is gamma. So this is actually back to front now. Good that we did this. Smallest will be gamma. I'm going to do it like this again because it's easier for me to remember. Radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. You can write the whole thing. I'm not going to write it. I'm just going to. Yeah, so there you go, very nice. Smallest wavelength to largest wavelength. Perfect. Let's continue onward now. We now need to find the magnitude and direction of a current passing through this resistor. Okay, so first things first, how are we going to solve this? What is the formula we're going to use for this? We have V and I. So, well, current, that's easy. That's just V over R. 4 over 20. 4 over 20 is 0.2. So C and D are wrong. So now we need to figure out the direction. All right. Fuel is coming out of the page. This bar is moving to the right, so I'm catching more dots. That means it's getting stronger. There are more field lines coming out of the page as I move the bar. And my area will increase. If that's the case, if my area is going to increase, it's getting stronger. Stronger. Remember, stronger, that means it will be in the opposite direction. The induced field will be opposite this. Stronger, opposite. What's the opposite of that? That is an X. We will have X. So that'll be X. What is X again? If you've forgotten, X is always clockwise. So we're going to pick clockwise. So clockwise, I'm going to follow the clock around this way. This is clockwise. I'm going in a circle, a full circle. And it's going from Y to X. It's going up the resistor, along and down. This is how clock works, right? That's the way it's doing it. Like that. So that means it's going to be B as the answer. Very nice. Okay. Next, what speed would this length of wire have to blah, blah, blah. Trying to find induced EMF. Okay, well, I can see that's the EMF formula. E equals BLV sine theta. Do we have this as perpendicular, isn't it? Now, what speed do I have? It didn't mention, so we're going to assume it's perpendicular. I didn't mention it, so I'll just write sine theta, why not? So we need to find the speed. So what do we have? We have the EMF of 10, the magnetic field 2.5, the length was 0.2, multiplied by V, which is what I need, times sine 90. You can write it if you want. I'm going to ignore it because sine 90 equals 1, so I don't need to write it. This is enough. And if you do V equals, you'll get your answer. You should get 20, and the speed is meters per second. Don't forget the units. Now what's happening here? EMF is induced in this wire. Same idea, but this time I need EMF. So this is BLV sine theta. Is there an angle? Nope, it's perpendicular. Moving up and moving to the right, that's perpendicular. So that's perfect. So I'll directly go ahead and put the numbers in. Where's the B? That's 0.30. 0.30. Multiply that by the length. The length is 0.75. That's in meters. That will be the length. The speed is meters per second, so that's 16. Sine of 90, no need to write it, and you'll get 3.6 volts. Very good. The wire is part of a circuit, and with the total resistance, what is the current? So we're going to find the current. Okay, so I equals V over R. What's the problem there? That should be easy. 3.6 over 11. 3.6 over 11 in a calculator, 0.33 amps. That'll do. Alright, so I'm going to move over to transformers in the next video because, oh actually no, I can finish it now, it's not that long. So let's go ahead and do transformers. Over here, is this a step up or a step down transformer? Step up usually means there's more coils on this side, so my voltage can increase. Step down will be less coils on this side, the secondary side, so the voltage can decrease. More coils, more voltage. Less coils, less voltage. So in this case, I can clearly see that there's more coils on the right hand side. Otherwise, if I didn't know, the input was 30 turns and the output, here is the primary, and the output is 750 turns on the secondary. So it's step up, more turns in secondary. You could also say more voltage in the secondary as well, but we don't know it. Don't know the comparison yet, but we do know the comparison between these two. We can find the voltage, that's fine. We can easily go ahead and find that voltage. We can just do our rule, and we can do NP over NS equals VP over VS. And by the way, you can write it any way you want. You can even write NS over NP equals VS over VP. It doesn't matter how you do it. As long as the S and the S is together, the P and the P are together, it's fine. You can even flip them around. You can even do VP over VS equals NP over NS. So I don't know how your teachers will be doing it with you, but that's either way is fine. I've written it like this, so I'm going to keep it like this. I'll get rid of that. And I'm going to keep it like this. So NP over NS. My NP was 30 over NS. NS was, what was it again? 750 equals VP. That's what I need to find. Over VS, which is the secondary, 4800. Shift solve, cross multiply, as you like. You will get 192 volts. If the power is equal to the power of the input, that's fine, so that's good. Because that P equals P, basically. That's IV, IV equals the secondary IV, ISVS. This is what we can do. We're trying to find the input current. You can go ahead and calculate the power, and then you can do I is P over V if you wanted to, but this is a way that they've given us. We can do it like this, it's not a problem. I'm trying to find, what am I actually trying to find? Input current. So input current will be this one, IP, multiply that by the voltage in the primary, which we now know is 192, equals the secondary current, which we have, the secondary current, which was, what was it again? 15 milliamps. So 15 milliamps means 15 times 10 to the minus 3, I like to write it every time like this, multiply by Vs, the secondary, which was 4800. Okay, shift solve, you can go ahead and find your IP. You'll find your IP, it should be about 375 milliamps. So 375 times 10 to the minus 3 amps. Or you can keep it in milliamps, that's fine. Okay. So what's happening here? Explain why an electromotive force is induced in the secondary coil. So the reason this is happening is because this is connected to an AC source. An AC source means current will flow, it's going to go one way, not that way, that's eddy currents. It's going to go one direction and it's going to return, back and forward, back and forward. It's going to keep changing direction. As it's changing direction, that's a changing field, changing flux, that will induce an EMF. So AC changes current direction. This induces an EMF. This means it's a change of flux, but I don't think you need to write too much. This induces EMF, which will create a current. Yes, so the changing the current direction is important because that means the field is changing. I should probably say that. Changing the current direction means change of field. Change of field. That is the reason, because of this change of the field. It induces an EMF. Is this transformer step up or step down? Well, I can see that the secondary coil has less numbers of turns already, so it's definitely going to be step down. Step down. Less coils on secondary. Sorry, I'm kind of rushing because this video is getting a bit too long now. What is the potential difference in the secondary coil? So we'll do it then. NP, NS, VP, VS. So NP, primary coils is here, 600 turns, 600. Secondary coils is 300, makes sense because it's supposed to be less, it's a step down. Equals VP, do we have the VP? Yes, supply voltage must be VP, that's my supply, input 220 over, I need this, VS. Shift solve, rearrange, you will solve it, you will get your number, and that number should hopefully be 110 volts. Now you're trying to find the current. You can again solve for power and then solve for current, or we can go ahead and just do IV just like before equals IV secondary, and we can go ahead and solve that this way. You can do it the other way as well. I'm not going to do it both ways because of the time, otherwise I would have shown you both ways. Anyway, the current in the secondary is this. We need to find the IP, multiply by VP, which was 600, equals IS 1.5 multiplied by VS, which was the secondary. What was it? And that wasn't no 600, that's not the current. What's this? This is the voltage. The voltage was 220 volts. And this was 1.5 times this, the new one that we figured out, which is 110 volts. So shift solve, rearrange, I will be 0.75. Okay, we are done. Thank you.